So my title has a really long title on the sheet of paper, but really the spell checking part is just a case study. What I really want to talk about is optimizing the execution of code. First, to introduce myself, I go by Q. A lot of you can all call me Q, that's fine. I got that nickname from my brothers because I really liked Star Trek. And then my first job out of school, I worked making the technician's job easier. So I was nicknamed Q there because of the James Bond reference, because I made all of the gadgets that made their job easier. I'm a certified architect, LabVIEW champion. I currently work at TestRact as the task architect. I'm the creator of the Q Control Toolkit, and I'm a Harry Potter fanatic. One of the things, if you all noticed, we all got quotes on the back of our badge. And Laura actually had my quote in her presentation. My quote is, "Any sufficiently advanced technology is indistinguishable from magic." They assured me that our quotes were random, but this is a perfect quote for me. And I'll show you why, because here's some of the things that my wife and I like to do. I actually bought the Harry Potter car and had it shipped from England. It's actually a left-hand driver. There's my wife and I's Instagram account for all of our Harry Potter adventures. We can talk about that after. I'm still paying for it. Here's another project. This is a cool one. This is actually programmed on a Raspberry Pi with LabVIEW. It has Arduinos interfacing with it, and so it's got LabVIEW, Python, Arduino C, everything. It's a little hodgepodge of everything. And so this, if you know about Harry Potter, there's a family called the Weasleys, and they have a clock that tells where all of the family members are. And so this one is all of my family members, and it works on the GPS of our phones and tells where all the family members are. And so that was a fun project to do. So here's what we're going to talk about. I'm going to give you some information, and then we're going to play a game, and if time, there'll be some more information, and then there'll hopefully be some bonus rounds. We'll see how time permits. So first off, let's go over the information stuff. So talking about optimization, probably you could break it down into more categories than this, but I broke it down into 7 categories. And I'm not going to go through this. I'm going to go through this pretty fast. I have notes and stuff in here that when you get my slides, you can read more into it. So consider part of this, homework. But going over quick on these categories first. So for our algorithms and loop, so when I talk about the algorithm and loop optimization, you're talking about wanting to do as few of iterations as possible. You want to use efficient data structures, avoid memory leaks, that sort of thing. For the memory leaks was on this one, sorry. So the memory one, this is the appropriate data structures, optimize your memory access, and that sort of thing. I'm going quick through these because I want to get to the fun part, which is the game. So concurrency, think about multi-threading processes, synchronization, don't create bottlenecks that cause things to go down just one stream, leverage asynchronous behavior, asynchronous programming. VI configuration, this is where you don't want your front panels to update too often, or you want to defer panel updates, that sort of thing. Configure your system priority, those kind of things. I/O optimization is, minimizing read and writes to disk, or use efficient data formats. Consider caching data or buffering data. So there's a lot more information on my slides than this, but that's okay. I'm going to just get through this, and then we'll do the fun stuff too. So code profiling and analysis, this is where you want to start looking for hotspots, identify the bottlenecks. This is where you might use the desktop execution trace toolkit. I'm going to show you some benchmarking type things as part of my presentation as well. And then finally, platform specific, this is optimizing for the platform, FPGA, real time. Consider your architecture in that. So could be a whole presentation of itself, and I just covered it in 3 minutes or whatever. So do some homework and download my slides later, and you'll get some more information. So benchmarking, here's a nice definition of benchmarking from ChatGPT. Thank you, AI, because whatever. Had ChatGPT write it for me. I'm not going to read that, but suffice it to say that benchmarking is a way to create a baseline that you compare against, and you want to optimize for, I don't know, like time or CPU usage or other things. And so for this, and then as part of benchmarking, I came up with 7 rules of thumb that you want to do when you're considering benchmarking. So first off, usually when you compare numbers in benchmarking, by themselves they don't mean anything. You usually have to compare like items together. You know, you want to compare the apples together. You can't compare the apples and oranges together. You have to run in a consistent environment. For example, I can't do benchmarking, say, on my laptop and on my desktop and expect those numbers to compare. Use multiple runs, especially if you're like in a Windows environment. You want to run something 1,000 times, 100,000 times, and take a time average. Because if you just run it once, the variability of those runs are going to widely vary depending on whatever Windows decides it wants to make a priority at that time. Isolate variables. This is testing only one thing at a time. You want to limit it down to, okay, I'm going to do this particular thing. I have some examples that we're going to use in the game here. Use representative workloads. I mean, if you don't do something that represents what you're trying to test, then the numbers don't mean anything to you. Like, one of the examples I'm going to show is reading in a dictionary. If I don't go read in a sufficiently large dictionary, like 70,000 words, I only read in a 10-word dictionary, well, that's not a good representation. Measure relevant bookmarks. This would be like, or relevant metrics. This would be like, you know, for this example, I'm wanting to make fast running efficient code, so I'm going to measure time. Measuring, you know, CPU usage might not be the metric for this case. And then document your conditions. If you can't reproduce what you wrote for your metric or for your benchmarking, then it doesn't help at all. So here's my area of focus. So out of those categories, I chose some things that I wanted to focus on. And ultimately, in this case study, I'm trying to make code that runs efficiently so that the user doesn't notice a significant amount of time in between interactions for processing. What came about for this is, yeah, as Jörg and several other people have mentioned, writing toolkits for sale to LabVIEW developers doesn't help, or is not a very good business practice. I wrote a documentation editor 10 years ago and put it up on the LabVIEW Tools network and sold it for a cheap $75 and sold exactly 5 licenses. And one person said, well, I will buy it, but not until it has spell checking. And so that's what got me into this whole idea of creating a LabVIEW runtime spell checker. And so as part of creating this, I'm like, well, it needs to run fast, you know? So I went through all these things. I wanted to choose the most efficient algorithms. I wanted to make sure that I was using the right data structures and that sort of thing, and that's what we're going to talk about today. So there's the information part. Now, as part of my rules of thumb for benchmarking, here's my documented conditions. So this is the resources I have on my desktop computer at home, and so that's what we used. I had a dictionary that had 76,920 words, US English spelling. I think I got that from the VI Analyzer, because it has a built-in dictionary. I think that's where my dictionary came from. I can't remember exactly. And then I performed a spell check on Around the World in 80 Days by Jules Verne, as published by the Project Gutenberg, because that's open, free thing that you can get. It consists of 67,322 words, and it's the UK spelling, which is good because I want to have things misspelled when I'm checking. So, you know, no extra U's. You put Z's in the right place. You know, let's spell it the proper American English way. All right, and then most of the time, I did 1,000 iterations for each of these. So these are the different pieces that I broke up the spell checker into, and we're going to go over each of these. So read the dictionary, split the dictionary into words, load the dictionary, remove punctuation, split the text into words, look up the words in the dictionary, and then if time, we'll talk about determining suggestions. So here's how we're going to make it a friendly competition. I should have handed these out beforehand. I forgot. So pass these out nice and quick. These are a scorecard. Oops. Let's not skip ahead. Okay. So here's how the scoring is going to work. We're going to get scorecards handed out. Each section that I described earlier has anywhere from 3 to 8 different ways that I decided how to do it in LabVIEW. And I'm going to show you the code for each of these. And you're going to then rank it from 1 to however many options there are in that round. And what we're going to do then is you're going to say, okay, let's say I thought the third one was the fastest. And then I reveal the scores, and you find out that you marked the third one, or the third one ends up being the fourth fastest. Well, then your score is 4. And ultimately, you want to get holes in one. You want to guess in all of the first place ones, all right? And so ultimately, by the end, you want to get 1 on each section. And then the fastest scores, I've got Harry Potter rubber duck for your rubber ducking troubleshooting sessions. His name's Harry Ponder. So first place winner gets this and one of these. I've got 3 for first place, second place, and third place, Raspberry Pi Pico W's. So for your guys to go make your own mind reader or your own Harry Potter Weasley clock or whatever. Does everyone have one? Who doesn't have one that wants a scorecard? Now, a couple of you probably should self-eliminate yourself. You know, Darren, I'm talking to you. Greg, I'm talking to you. You guys can decide if you're one of those. But feel free to participate anyway, just for the fun of it. Okay. So the first one, let's see, can I have one of those papers? Where did they? It'll be easier for me to read off this. So for the first round, reading the dictionary. So I have, how many different ones here? I have 5 different ones here, so rank them 1 through 5. But here's the first one, reading the text by binary. So basically I have a text file that is my dictionary. It is essentially a 1D array kind of thing where it's 1 word on each line separated by a line feed. But for this case, it's all in binary. It's not a human readable file. Okay, next one. What? Yeah, so rank this one 1 to 5 from fastest. 1 is fastest. Yep. So this one now is a text file, human readable file, but you're using a spreadsheet string to read it in. This one is kind of maybe a misnomer kind of thing, because you're not really reading in the dictionary. You're actually just doing a query and reading all of the words from the table, but it's an SQL-Lite query. This one is doing it with just the query. So the difference is this one has the open and close as part of the 1,000 iterations. This one has just the query as the 1,000 iterations. And then this one's just a regular text file. So go ahead, rank them from 1 to 5. I'll give you a few seconds. Do you have any, you can ask questions on the code if you need to, but this one's a fairly simple one to get started. Okay, anybody need any more time? Are we good? Okay. So here's the score. Binary's the fastest. So depending on which one you ranked number 1, that's the score that you give yourself for that question. Okay? So there's some caveats to this one. The dictionary read as an array, the spreadsheet string reads it as an array rather than as a text. So later on steps, we don't have to actually split the string up. Like I said, the database doesn't actually read the entire dictionary because it's already in a file. I used SQLite, which is the file-based dictionary like we've heard previously in some presentations. So if SQLite was your number 1, then your score would be 5. As an example, yeah. So hopefully you got a hole-in-one, golf scoring. Well, you're supposed to rank them so that you can get a score for that question. And then we'll add those up, and then the lowest score wins. So if you get all holes in one, you should end up with 6 points in 6 rounds, all right? Okay, can we move on to the next one? Are we still having confusion? Are we good? Okay. Splitting the words into dictionary. So this is now, we've read the string in, but our dictionary is one humongous string. And now we need to split the words up by the carriage return or the line feed or whatever. So I have 1, 2, 3, 4, 5, 6, 7, 8 different options for this one. So you'll rank them 1 through 8. Okay, first one, delimited string. So this is a VI, and it's a built-in VI that you can find in the string palette, and you just put it into the delimiter, and it just spits out the 1D array. Match pattern. So this one is doing a match pattern here, and it's finding out where the next line feed is, and then it's doing a substring up here to actually pick out the word. This one is pick line. So I don't know how many people have used the pick line primitive, but it's in the string palette. And basically, it could just loop through until it gets an empty string and writes out the 1D array. Okay, this one is scan for tokens. And so it is scanning for tokens here. Oops. The difference between that one and the next one is that this one caches something here, has a true right there. Other than that, it's pretty much the same. Here, I'll show them again. This one's the scan for tokens. This is the scan for tokens with cache. This one is a split and search, but it does it by index. So it's keeping track of the index here, as opposed to the next one, which is keeping track of the string. But it's both using the split and search. And then finally, the spreadsheet string. Okay? Give you a few seconds to decide. All right, anybody need any more time? Okay. Yeah, too many options on this one. I had too much fun coming up with options on this one.
Apparently.
Okay, let's count down. 5, 4, 3, 2, 1. All right, we ready? Okay. So the split and search, but you're shifting by index, was the fastest. And you can see the pick line, do not use that one. The pick line was terrible. I only ran it once because it sat there forever and ever, and I was like, what's going on? And then I ran it just once and found out that it was taking 30 seconds to run. Yeah, that's what I figured. It starts from the beginning every time, is what Greg says. Okay. Got your score for that one? Ready for the next one? Okay. Okay, we're good? All right. Next one, loading the dictionary. So the idea behind this one is now you have your dictionary kind of split up. You're going to load it into whatever mechanism you're going to use to look up the words later. And so I have 4 options: array, set, SQLite, or SQLite, and variant. And actually, I'm going to give you a hint. There's a little bit of a trick to this question, because I'm only going to show you the set and the variant in code here, so keep that in mind. So here's the set. I'm basically taking a 1D array and I'm loading a set. Simple enough. This one I'm taking a 1D array and I'm loading it as a variant attribute, which was the old way to do kind of set-like stuff. So, what do you think it is? 1 through 4. To use it. How fast did it run? And I run it 1,000 times and then take the average. So it's how fast does it take to run essentially one iteration.
Wait, what is
huh?
array?
What's that?
What is array? He's not going to show us that. He already said that.
Yeah, I'm not showing you array or SQLite. So keep that in mind in your ranking. You probably only really want to rank, set and variant.
But this is loading, not searching.
This is loading, so it's taking the dictionary and basically it's running that VI that I showed you 1,000 times. Okay, are we good? No? Yes? Okay, well I'm going to go ahead and move on then. So this one, this is why it's a trick question. The array, it's already split up, and later on down the road, on some of these examples, we're going to be using the array as the array. On some of them, we're going to be using the set. On some of them, we're going to be using the variant. And then the SQLite, well, it's already loaded into the table. So there's no extra loading necessary. Okay, ready for the next one? So now I've got my text. I've got my around the world in 80 days. It's got punctuation in it. I don't want the punctuation when I'm starting to split the word up, so I want to remove the punctuation out of it. So I have 5 different ways I did this. First off, I basically had an array of the letters I wanted to keep as U8s. Yeah. The letters to keep. Yeah, I don't know about readable or whatever, but whatever. It is what it is. So anyway, it is looking at it's changing the entire text into U8. It's checking to see if it's in that array. If it's in the array, that's what the OR is. If it's any of the items in the array, then it keeps it. If it doesn't, it replaces it with the 32, which is a space. What's that? Oh, well, yeah. All of these I could have made parallel. Some of them I could have inlined. I'm not comparing that part at all, just for the sake of ease of comparing this. this out. Yeah, this one particularly could have been parallelized because it's not got any dependencies on previous iterations through shift registers. Okay, this one, it has the entire U8, 0 through 255 in the array, but I only kept the things in the array that I wanted to have, and everything else is replaced with the 32 for space. So essentially what I'm doing, I'm indexing through, and I'm either picking the actual letter that I want to keep, or I'm picking 32 out of that array. Okay, you got that one? Next one, this one I'm searching for a space, and then I'm replacing it with whatever I want to replace. Actually, I'm searching for the letters to replace, which is anything I don't want to keep. White space, punctuation, numbers, all of that stuff that I don't want to keep, and I'm replacing it with a space. That's search and replace. Search array, so this is searching array again of letters I want to keep, trying to find it. If it finds it, then, or if it finds it in, let's see, I think I've got that labeled wrong. I think this is letters I don't want. Okay, I'm confused now too. Oh, okay, it's the less, yeah, it's the less than here. That's my problem. If it is true, that means it wasn't found. So I replace it with 32. If it was found, then yeah.
He needs a label on that 32.
Yeah, well, I'm sure there's a lot of things that are wrong, but we'll ignore that for the sake. Okay, and then going along, this is using the VIM, the sorted array, to kind of do almost the exact same thing. Okay. Okay, are we good on this one? Ready? Okay, here we go. So the index, the direct index is the fastest. You can index through arrays really fast. Searching through arrays is somewhat slower. Okay, you got your score? Ready to go on? Okay, splitting the text into words. So now that we've gotten rid of the punctuation, we have nothing but text and spaces. And now I want to split my text up into just a bunch of words. So we have, I think, 8 on this one. So this one is the match pattern. So it is matching the space and then picking the substring based on where the space was.
Is this the same as 2?
What's that? This is going to be pretty close to the same as 2, but there is some differences. So just keep that in mind when you do your score, that this is really close to 2. So I might give you a freebie here. Okay. Scan for tokens, pretty much the same, except now, like you said, in 2 we were looking for a line feed, now we're looking for spaces. This one is scan for tokens, but we're scanning our tokens has all the punctuation and everything still in it. So we're using all of the tokens, not just space. So the caveat for this one is we didn't do the punctuation remove step. We went straight to this step. And then you have with cache, and then you have all of it with cache. So that's the only difference between those. Then you have the shift by index again, and then you have the shift string again, and then you have the spreadsheet string. All right. So this one you probably got done a little bit faster because, yes, like Matt said, it was pretty similar to round 2. So I'm going to go ahead and put up the score. And yes, it was the shift by index again. So you might have gotten a freebie there. But you can see there's some that are really close. And give or take a run of this, you might have some variability. Like, look how close the shift by index and the shift by string is. You know, depending on if Windows had a good day on one run and a bad day on the other run, you might have those have those swapped. Okay, let's go on to round 6. Look up the words in the dictionary. This one's probably one of the more important steps, right? Because now we've got the words split up. We're going to go look and see if it's in the dictionary and determine, essentially almost like a pass or fail, is it spelled correctly, therefore it's in the dictionary, or is it not spelled correctly because it's not in the dictionary? And we have 7 different options for this. So the first one is looking it up in a set. So we brought in our set from the previous step. We brought in the words from the previous step, and we're checking to see if it's in the set. This one, we're doing a search in an array, but we're going to assume that the dictionary array has already been pre-sorted. So it's in alphabetical order or that sort of thing. One thing to keep in mind that I didn't show in any of these steps is I converted everything to lowercase. So keep that in mind too. We're not looking up case specific. This is only a lowercase. This one is doing a query to see if it's in my table, my dictionary table. This one is it's kind of 2 parts. It's creating a temporary table. It's putting in all of my words in the temporary table. And then it's doing that nested query there to decide if the word exists or not. And then this one is similar. It's doing a temporary table, but instead of doing a nested query, it's doing a left join there to determine if the word is in the dictionary or not. And then we have the regular search. Basically, if it was assuming it was unsorted now, the unsorted search, and the variant lookup. So go ahead and rank yours 1 through 7 on that one. Okay, are we done? Ready? So there's the scores, the sorted search. Now you can see the reason why I ended up doing the table join is because the other 2 were crazy slow. And I'm like, wait a second, this is a database. There's got to be a better way to do this. And then I found the table join method, which is a lot faster, but it still doesn't beat the sorted search. Now, why is the sorted search so much faster? Well, I don't know exactly. Greg can probably tell us what it's doing under the hood, but I assume it's doing some sort of binary search. So it's not doing, now if you know, the regular search primitive always starts from the front and searches down until it hits the thing and then it exits. The binary search, obviously, it can do some bifurcation of the array and find things a lot faster. Okay. So I might not have enough time to get to the rest of this, but let's see what your scores are before I go to bonus rounds. We got 12 minutes? Oh, we might have some time. So add your preliminary score up. First off, has anybody got 6? Like they got holds in 1 every time? No one? Okay, how about, I don't know, how should I do this? 6 to 10. How many got less than 10? So we cut, yeah. I forgot your name, I'm sorry. Jim, yeah. The other Jim. So we've got 2, right? Any third person? Oh, and Jeremy. Are you playing along then? You didn't.
Yeah, I'm not eligible for prizes. Yeah.
You're not eligible for prizes, so we need one more person. Okay, what about less than 15? Okay, there's a lot. How about, who got 11? Oh, you have 9? Oh, so we have our 3. So you have 9, Katya, you have 9. What I chose as number 1, you write the score of what you chose it to be. And then you add those up. So go ahead and rescore if you need to rescore. So I'm trying to determine if we have a top 3 already or if we have a tie. Okay, now that you've rescored, do we have a top 3? Katya, are you still one of the, what do you have? You still have 9? And you still have 9, right? So what was your name? Sean? So Sean has 9, Katya has 9. Anybody else? 9, 10. So 10. So there's our top 3. Okay. Good job. Okay. With the little bit of time we have left, you guys can come up afterward for the prizes. For the little time we have left, I wanted to talk about determining suggestions. Now, there's a whole kind of science to determining whether a suggestion is good or not. And so some more information. There's these 2 guys named Damerau and Levenstein who came up with the Damerau-Levenstein distance. And basically they came up with this idea that however many steps it took to take one word and turn it into the other word would give it a rank of how closely related those 2 words are. And the steps are deletion of a letter, insertion of a letter, substitution, where you just took one letter out and put in another letter, or transposition, where you took 2 adjacent letters and swapped them. And it says these 4 operations constitute 80% of misspellings that could take place. So, for example, if you wanted to compare one versus own, well, it is one transposition to move the N and the E, and then it is one substitution to replace the E with the W. So that is a total cost of 2. From 1 to tops, you have, actually that should be, I think that should be tone to tops. No, it is 1 to tops, because the first step is you insert a T on the front. Then the next step, you did a substitution and you replaced N with P. And then you did another substitution and replaced the E with S. And then that's the steps you would take from 1 to tops. So, for example, here's a distance from elephant to relevant is a minimum distance of 3. This is, if you go Google Damerau-Levenstein, I think this is the graphic it shows at Wikipedia. I just stole it from there as an example. So the naive approach to compare your misspelled word then to try to figure out if one of the dictionary words is a possible substitution for that, you have to loop through and compare them all and do all of those calculations and find out who has a distance of 2, or less. Basically, 2 catches most of the misspellings and gives you a pretty good suggestion list. But I found if you did it through this naive approach, it took approximately 22 minutes to spell check around the world in 80 days. So not good. Another suggestion came up by a Google data scientist named Peter Norvig. I guess I'm saying that right. He pre-processed all the dictionary items through a distance of 2. So basically calculated all of the different deletions, transpositions, insertions, substitutions, and did that for one set, and then turned around and took that bigger set and ran it through the algorithm again, and did a pre-calculation step, essentially. By doing that, well, let's see. Actually, this was the bonus round, so we'll just run through these. So this was doing the deletion step, coming up with taking every string in the dictionary of our 76,920 words and doing the deletion. So there's deleting from an array, replacing string subset, deletion, see that's a replace substring, string subset. So we'll just let you guys yell out now. Which one do you think is the fastest? No one wants to speak up. Greg, which one's the fastest?
We'll say
String subset. Oh, but it was close. You know, like I said, one Windows run could probably swap those two. Okay, transpositions. This time, I'm transpositioning 2 letters in the word. And so in order to create all of the different variations, I have to go through and do it with the first letter, second letter, third letter, all the way through and create a big, long dictionary list. So here's in place. So I'm just indexing the next 2 letters, swapping them, and then putting them back in. This one's doing a replace. And this one is basically it's cutting the stuff before, the stuff after, and the 2 letters that you want to swap, and then it's using the reverse string to swap them. So what do you think is the fastest in this one? It's close. Run it, yeah, we could run it again, but I on my desktop with me, it's kind of hard to take on the airplane. Okay, let's go to, and you can see each subsequent one of these, like if I go back, you can see this created 500,000 plus entries. This one created 600,000 plus entries. And this is only going through once, not going through it again, doing two iterations of this. So let's go through, let's see. So, and then this one's creating 16 million entries for substitution. This is substituting every letter once. So we have in place again, where it's doing an in place on the array. This one's doing a replace array subset. This one's doing a replace substring. This is doing a string subset. So which one do you think is fastest on this one? I know I'm going through the code quick. We're almost out of time, but I wanted to just show this because it's interesting. So the replace substring was the fastest. Okay, now this one's an insertion where you're inserting a letter. This one created 18 million, almost 19 million entries. So we have basically the same kind of things. This is an insert into the array. This is a replace array subset. Now this one was one that Stephen showed me. So this is more computer science-y than most, because you're doing a whole bunch of flipping of stuff, rotating of stuff in the array. So, and then string subset. So given that, which one do you think?
computer science-y stuff.
Yeah, the computer science-y stuff won that one. The rotate array won that one. Okay, so if you did all of Peter Norvig's stuff and you came up with all of these options, it ends up with so many search terms. Now what you're going to end up doing is you're going to end up finding a lot of repeats, and you're going to get rid of the repeats and narrow it down. But still, that took 19 minutes to do the pre-processing of that. So there was this third approach called symmetric delete spelling correction. And so instead of doing all 4 of those steps, you only do the deletion step. And you're going to come up with enough ideas that you're going to come up with a pretty good suggestion list. And so doing this, you can do this still in a pre-calculation step. You could actually cache it depending on your dictionary. So you could cache all the deletions and keep that and then only process like a user dictionary or something like that. And so the pre-calculation step of that only took about 21 seconds. And so this is basically the steps that you end up going through when you're doing this. And so there's how it calculates. When you actually go say, so this is if the user, let's say everything's already preloaded, you know, all of the pre-calculations done, the user now right-clicks on the word that's misspelled, it's going to take approximately 337 milliseconds for it to process and come up with the list for the user now. So how good are the suggestions? Well, here's some idea. Given I went back and I compared, given the suggestion list, is the word actually in the suggestion list? And this is about how good it did. So yeah, the symmetric deletion didn't do as well as the other ones, but given the trade-off. Now, there's other things that you could optimize with this, obviously. There are parallelizing you can do. There's in-place kind of things you can do. There's maybe some more statistical analysis you can do by comparing the words around it. There's a whole bunch of things. But I wanted to make this something really easy and implemented all in LabVIEW. And so I am going to publish my runtime spell checking eventually, hopefully not too soon after we're done at this event. And you'll be able to download it, and you'll be able to pass it a string reference or pass it the actual string, and it will do the spell checking for you. So any questions?
You used 32-bit LabVIEW. Is there a reason you did that? And was there a difference in 64-bit LabVIEW?
I didn't run this in 64-bit. I'm sure there would be.
It's already over budget.
Yeah. No, when I did this the first time, I did it all in like LabVIEW 2018 or 2017. It was 32-bit. That's just what I had back then. I just left it in 32-bit for LabVIEW 2020 this time. Could I run it in 64-bit? Yeah, I probably should go back and do that exercise, but I didn't. Would I get different results? I'm sure I'd get different results, but they might still compare. They might still be comparable. It might be faster overall, but at least that's what I assume. I don't know. Do you have any thoughts on what would be different if I did? No? No? Okay. So I guess that's all the time for questions because I ate up all the time. But we did make it through it all, so I was surprised with that. So please ask me questions afterwards if you have questions. Thank you.